Hello all, welcome to the course CS401 Computer Graphics. In this video we are going to see polygon clipping, which is a portion in module 4. Polygon clipping. We've already seen point clipping and line clipping in the last module. To clip a polygon, we can simply modify the line clipping procedures discussed in the previous module. That is, a polygon boundary processed with a line clipper may be displayed as a series of unconnected line segments depending on the orientation of the polygon to the clipping window. So this is a figure in which a polygon is clipped using line clipping algorithms. Okay, so when you are using line clipping, you can this line segments are displayed as unconnected line segments like this. Okay, so after clipping, this is the figure that you get. Okay, so but what we really want to display in a polygon clipping is something like this. Okay, so here is an example figure. Here you have a polygon which is clipped using a polygon clipping algorithm. So this should be the figure that you get. That is, for polygon clipping, we require an algorithm that will generate one or more closed areas that are then scan converted for the appropriate area fill. Okay, so the figure should be something like this. The output of a polygon clipper should be a sequence of vertices that define the clipped polygon boundaries. Okay, we are going to see two algorithms that is used for polygon clipping. First one is Sutherland-Hodgman polygon clipping algorithm, and the second one is Wheeler-Atherton polygon clipping algorithm. Okay, so Sutherland-Hodgman polygon clipping algorithm, we can correctly clip a polygon by processing the polygon boundary as a whole against each window edge, that is clipping window edge. Okay, so this could be accomplished by processing all polygon vertices against each clip rectangle boundary in turn. That is, the figure shows how it is done. That is, you have a polygon here. So here this polygon is shaped like a star. First the polygon is clipped against the left boundary of the window. This dotted lines shows the clipping window. So here first it is clipped with the left boundary. So you get a set of vertices after clipping with the left boundary that is given to the next clipping. So here it is clipped with the right boundary, then it is clipped with the bottom boundary, and then the top, and so you get the clipped figure. Okay, so beginning with the initial set of polygon vertices, that is, here you will have an initial set of polygon vertices. We could first clip the polygon against the left rectangle boundary to produce a new sequence of vertices, and the new set of vertices could be successively passed to the right boundary clipper, then the bottom, and then the top boundary clipper. Okay, that's how a Sutherland-Hodgman polygon clipping algorithm works. Okay, so when you do this, there are 4 possible cases when processing the vertices in sequence around the perimeter of a polygon. Okay, so we are going to see the sequence of vertices around a polygon, and there can be 4 possible cases. Okay, when you are processing the vertices. So that is shown here as each pair of adjacent polygon vertices is passed to a window boundary clipper. we make 4 tests. Okay, so first test is that um, first test is if the first vertex is outside the window boundary and the second vertex is inside. This is shown here. Okay, so here you have a vertex v1 and a vertex v2. Here the first vertex v1 is outside the window boundary and the second vertex v2 is inside the window boundary. Okay, so out, in. So in such cases, what you do, you discard this v1 and you save only this vertex v2 and also the intersection vertex, that is the intersection of this line with this window boundary, that is v1 dash. So v1 dash and v2 is saved and v1 is discarded. Okay, then second case is that, or the second test is that if both the vertices are inside the window boundary. Here you can see a vertex v1 and another vertex v2. v1 v2 are adjacent vertices and the v1 is inside the window boundary and v2 is also inside the window boundary, that is in pair. So here what you have to do, you have to save only the vertex v2. Okay, only the second vertex. Then the third case that can happen is that whether when the vertex v1 is inside the window boundary and the second vertex v2 is outside the window boundary. Okay, so in that case you have to find the intersection vertex v1 dash and you have to save only v1 dash. Okay, that is for in out case. Okay, and the last case is when both the vertices v1 and v2 are outside the window boundary. Then in that case you discard both of the vertices and you save none of them. So these are the 4 possible cases when you are processing the vertices against the window boundary. And here this is a figure that shows clipping against the left boundary along. Okay, so once you test for all the 4 cases and you process the vertices. Okay, so this is the cases that you have seen in the last figure. Okay, and once all the vertices have been processed for one clip window boundary, the output list of vertices is clipped against the next window boundary. That is, after testing all these cases, you get a set of vertices. You are saving some vertices, right? Here it is v1 dash, v2, and here also v2, and here v1 dash, and here none. So these vertices, these output of the after clipping with the left boundary, you get a set of vertices that is passed to the next window boundary for clipping. Okay, so this is the Sutherland-Hodgman polygon clipping algorithm. Okay, so step 1, you read the coordinates of all vertices of the polygon. Then in second step, you read the coordinates of the clipping window. Then third step, you consider the left edge of the window. Then fourth step, you compare the vertices of each edge of the polygon individually with the clipping plane. Then fifth step, save the resulting intersections and vertices in the new list of vertices according to 4 possible relationship between edge and the clipping boundary that we have seen in the last part. And then repeat the steps 4 and 5 for the remaining edges of the clipping window. Each time the resultant list of vertices is successively passed to process the next edge of the clipping window, and then stop. So this is basically the Sutherland-Hodgman algorithm. The method that we have explained now is illustrated in this figure. So initially the polygon consists of 6 vertices and it is labeled as 1, 2, 3, 4, 5 and 6 here. And after using the method that we have told, that is processing each vertex of this polygon sequentially, that is, first you take the vertex 1 and vertex 2. Here it is out out pair, so this 1 and 2 is not saved. Then you take the next vertex 2 and 3. So here 2 is out and 3 is in, so it is an out in pair. So you have to find a intersection point 1 dash here. So 1 dash, this point 1 dash is saved, and the vertex 3 is saved as 2 dash. Then you take the vertex 3 and 4, both are inside, so you save 3 dash, because 3, this 2 dash is already saved. 3 is already saved as 2 dash, so next you save 4 as 3 dash. Then you take 4 and 5 vertices, again it is in, so you save the vertex 5 as 4 dash. Then you take the vertex 5 and 6. Here 5 is inside and 6 is outside. So here you find intersection point 5 dash, and you save 5 dash only. Okay. This is how you find the new set of vertices after clipping with the left boundary. Okay, and so you get 1 dash, 2 dash, 3 dash, 4 dash and 5 dash as the output after clipping with the left window boundary. Then this 1 dash, 2 dash, 3 dash, 4 dash and 5 dash, these vertices are passed to the next clipping window boundary. So next you have to process with the right boundary. Okay, and then with the bottom boundary, and then with the top boundary. Okay, so this is how the Sutherland-Hodgman polygon clipping works. Okay, since all these are inside the all the boundaries, these 5 vertices will be the output after Sutherland-Hodgman polygon clipping. Okay, and we can eliminate the intermediate output vertex list. That is the output vertex list that we create after each clipping, that is after clipping with each boundary of the uh, clipping window. You get an output vertex list, which is a intermediate output vertex list. You can eliminate saving that intermediate output vertex list by simply clipping the individual vertices at each step and passing the clip vertices onto the next boundary clipper. Okay, and this can be done with parallel processors or a single processor and a pipeline of clipping routines. Okay, so an input vertex or a calculated intersection point, that is any point, is added to the output vertex list only after it has been determined to be inside or on a window boundary by all 4 boundary clippers. Okay, so that is shown in this figure. Okay, here you have a polygon v1, v2, v3, a triangle which is overlapping a rectangular clip window. So here we are using a pipeline of routine. So here the each vertex will pass through all 4, or each vertex, whether it is a these vertices v1, v2, v3, or the new vertices that is created by because of the intersection with this window boundary. All these vertices have to pass through this pipeline. Okay, so first the vertex V1 is taken, it passes through all the clippers, that is first left clipping, then right clipping, then bottom clipper, then top clipper, and you get an output. If it passes all the clippers, you get V1 as V1 here. So if you take V1, so this is our V1, vertex V1. You clip it with the left clipping boundary. So okay, so it is inside the left clipping boundary, so you can it passes goes to the next clipper. So here it is right clipping, it's again inside the right boundary, so V1 can be stored there. Then it goes to the bottom clipper, so it is outside the bottom clipper, so you eliminate that. So similarly, every vertex, every point has to pass through this four clippers, and if it passes all the clippers, here you get the output vertices. So after passing all these vertices through all these four clippers, you get V2 dash, V3, V, V3 dash, V2 dash, dash dash as the output vertex list. Okay, so that is the final output vertex list. That's how it works. Okay, so uh, this is all about Sutherland-Hodgman polygon clipping algorithm, and the next one is Wheeler-Atherton algorithm. Okay, so if you see the Sutherland-Hodgman polygon clipping algorithm, this Sutherland-Hodgman polygon clipping algorithm is only used works well only in case of convex polygons. Okay, so here this is an example of a concave polygon. Okay, so in this case, this is a concave polygon. For this, when it performs the Sutherland-Hodgman clipping, what happens is, see here you are clipping here and here, but there is a connection between this, but actual polygon there is no connection, right? So an extraneous line is created here. So this is not the it is not actually correctly clipped. Okay, so in such cases you can use the Wheeler-Atherton algorithm is uh, more efficiently or correctly clip this concave polygons also. It is good for convex polygons as well as for concave polygons. So since you wonder what is convex polygon and concave polygon, I'll just give you a difference between what is concave polygon and convex polygon. Okay, so here is the difference. That is, the convex polygon is a polygon where all the angles should be less than 180 degrees. So if you see this triangle, you can see that all the internal angles, see, all these internal angles are less than 180 degree. Okay, and there is no angle that point inwards. Okay, so there is no all the angle is pointing outwards. See, all the angles are pointing outwards. So such polygons are called convex polygons. And there are some other polygons with any one of the internal angles greater than 180 degree. Okay, so if you see this polygon, you can see that here there is a angle, an internal angle which is greater than 180 degree. Okay, so that means it is a concave polygon. Or to understand it very fastly, what you have to see is that in concave polygons there will be always a angle which is pointing inwards. See, you have a line, an angle which is pointing inwards. All others are outwards, but here one angle is inwards. That means it is a concave polygon. Or you can use a simple test, that is, you draw a line passing through this polygon. For in case of convex polygons, you in any way you draw a line in this passing through this polygon, it can pass only through two lines of this polygon. See, if you draw a line like this, it passes through only two lines of the polygon. If you draw like this also, it will pass through only two. Like this also, it will pass through only two lines. Okay, so that means it is a convex polygon. In case of concave polygon, if you draw a line through this, it will pass through only two lines. But if you draw a line through this, it is passing through four lines. Okay, so if the line can pass through more than two lines, then that means it is a concave polygon. That is a simple test that you can do to differentiate between a concave polygon and a convex polygon. Okay. This Wheeler-Atherton polygon clipping can be successfully used in case of concave polygon clipping. Okay, here the vertex processing procedures for window boundaries are modified so that the concave polygons are displayed correctly. Okay, so the basic idea in this algorithm is that instead of always proceeding around the polygon edges as vertices are processed, we sometimes want to follow the window boundaries. Okay, in case of this Sutherland-Hodgman polygon clipping, you take each edge of the polygon and you follow the polygon edges for processing. But in case of Wheeler-Atherton polygon clipping, you follow the polygon edges and sometimes you follow the window boundaries also. And which path we have to follow depend on the polygon processing directions and whether the pair of polygon vertices currently being processed represents an outside to inside pair or an inside to outside pair. Okay, so the polygon processing directions can be clockwise or counterclockwise, and based on this, and also whether the pair of polygon vertices is currently being processed represents an outside to inside pair or an inside to outside pair. Okay, and for a clockwise processing of polygon vertices, we use the following rules. That is, for an outside to inside pair of vertices, follow the polygon boundary, and for an inside to outside pair vertices, you have to follow the window boundary in clockwise direction. So that is how you process a polygon in case of a clockwise process. Okay. So here this figure shows how the polygon processing or polygon clipping is done using a Wheeler-Atherton polygon clipping algorithm. Okay, so first we make a list of all intersection points, namely I1, I2, I3 or V1 dash, V2 dash, etc. here. So you find all these intersection points first. So here it is V1 dash, V3 dash, V4 dash, V5 dash, etc. So that is the first step. Then you classify those intersection points as entering or exiting. That is here. Here it is a clockwise. This polygon is in a clockwise direction, processed in a clockwise direction. So each of this intersection points, that is, you take first V1 dash, you label it as whether as entering or exiting. You give some label E for entering and X for exiting. Okay, so you label the vertices as entering or exiting every vertex. So here V1 dash is an entering vertex, V3 dash is a exiting vertex, V4 dash is again an entering vertex, and V5 dash is an exiting vertex. Okay, so you label it accordingly. Then third step, you make two lists, one for clipping polygon, that is the clipping window, and the other for the clipped window, clipped polygon. Okay, so here you make two lists like this. So here it is for the clipping polygon. For clipping polygon, list is that is the vertices uh, placed in this list in the order A, B, C, D, V5 dash, V4 dash, V3 dash, V1 dash, and V1 dash automatically to A. Okay, so that order, it is a list of vertices of the clipping polygon is made, and similarly for a clipped polygon also the vertices are listed like this. So here it is V1, V1 dash, V2, V3, V3 dash, V4, V4 dash, V5, V5 dash, V6, and V6 to V1. Okay, so you make a list of clipped polygon and the clipping polygon. Okay, list of vertices. Then so you fill the both the lists in such a way that the intersection points lies between the correct vertices of each polygon, and that is the clipping polygon list is filled up with all the vertices of the clipping polygon along with the intersection points lying between the corresponding vertices. You have already seen that. Now start at the to be clipped polygon list or the clip polygon list. Okay, so you choose first the intersection point which has been labeled as an entering point. Okay, so what you do is you take the clipped polygon list and take an intersection point which is labeled as an entering vertex. Okay, intersection. So here V1 dash is an entering vertex. So you start from here. Okay, so V1 dash to V2, V2, V3 process, V3, V3 dash, and you check whether this V3 dash is in the clipping polygon. So V3 dash is here in this clipping polygon here. So V3 dash, and in clipping polygon it comes V1 dash. Okay, so it goes to V1 dash. So you get, if you see that order here, it starts from V1 dash, V1 dash, V2, V3, V3 dash. Then you go to the clipping polygon list. Here V3 dash, next is V1 dash. So you get these vertices. Okay, so this part is clipped like that. So V1 dash, V2, V3, V3 dash. So V3 dash, V1 dash. So this is the first clipping happens here. Then again we resume, and you find the next entering vertex in this clipped polygon. So first was V1 dash, next entering vertex is V4 dash. So you start from V4 dash, V4 dash to V5, V5 to V5 dash. V5 dash is another intersection vertex, which is an exiting vertex. So you go to the clipping polygon. Here there is V5 dash, V5 dash to next is V4 dash. Okay, so you have reached again back to V4 dash. So you stop there. Okay, so you get the clipped polygon, that is V4. We start from V4 dash, V5, V5 dash, V5 dash to V4 dash. Okay, so you get it. Then again you check for the another entering entering vertex. So here is no other entering vertex, you stop it there. So that is how this algorithm works. So you start at the clipped polygon list, choose the first intersection point which has been labeled as entering point, follow the point in the list, looping back to the top of the list in case the list ends, and keep on pushing them into a vector or something similar of the sorts, and keep on following the list until an exiting intersection point is found. And once you find an exiting intersection point, now switch the list to the polygon, that is that is a clipping windows list, and find the exiting intersection that was previously encountered. Now keep on following the points in this list until the entering intersection point is found. Point is found. Okay, and this vector now formed by pushing all the encountered points in the two lists is now clipped to polygon. Okay, and repeat this clipping procedure until all the intersection points have been visited once. Okay, so that is basically Weyler-Atherton clipping algorithm. Okay, so this works for concave polygons like this. Okay, this is a concave polygon as well as for a convex polygon also. Okay, thank you.